Hello and welcome to lesson 11.4 on graphing sine and cosine functions. Today's goals, we're going to be trying to graph and analyze sine and cosine functions. We're also going to be modeling periodic real-world situations with sine and cosine functions. Vocabulary that's important today is oscillation, midline, amplitude, sinusoidal for sinusoidal functions, and frequency. Okay, so let's get into it. Like other functions you have studied, trigonometric functions can be graphed on the coordinate plane. Sine and cosine functions are oscillating functions, right? That means they go up and down and up and down. The oscillation of a function refers to how much the graph of the function varies between its extreme values as it approaches positive or negative infinity. Okay, so if I have cosine of x versus, let's say 1.5 cosine of x, this 1.5 cosine x is oscillating more. It's got a greater amount of oscillation, the distance from the top to the bottom. The midline is the line about which the graph oscillates. So for this one, the midline would be just y equals 0. But if I wanted to lower that midline, I could bring it down. So you could bring it down to any point for that midline at 0.3 or something, right in the middle there. So that is our midline. The amplitude of the graph is the distance you are from the midline. So it says it equals half the difference between maximum and minimum values. So if we're going from 1 to -1, that's a distance of 2. That means our amplitude is 1. So it's always the distance from the center line, the distance from your midline to either the maximum or the minimum. So if I was to, for example, move this down here, that does not change the amplitude because we're not measuring from like y equals 0 down to the bottom. We're measuring from the middle of the oscillation and the distance from the middle. So it's going to be 1 no matter what. The only way to change that amplitude is to change that number in the front. 2, now I've doubled my amplitude from this midline to the maximum. I have a distance of 2. Okay, basically, every way that you can describe sine and cosine functions on a graph is pretty similar. So for example, the domain, they both have a domain of all real numbers. There's no angle that you can't use, that you can't take the sine over the cosine. The range for your standard sine and cosine is the same. So it starts from -1, goes up to 1. So that is the full range in the y direction for both of these. The midline is the same at y equals 0 for both of these. The period, the amount of time it takes for one full rotation, is 360 degrees for both of them. And the oscillation is the same. It oscillates between -1 and 1. So the only thing that's different is that sine starts at 0, cosine starts at 1. Okay, that's the only difference. For cosine, it's easy to remember because if you're starting at 1, you have to be going down. For sine, you just need to remember that we start at 0 and we head up first. So they're basically the same graph, just shifted to the side a little bit from one another. So sine and cosine functions, like other functions, can be transformed. You can use the graphs of the parent functions to graph y equals a sine bx. Okay, so they're saying that there's kind of two different variables that we might put in that would be factors, that would be multiplication. And these two variables are going to do different things. And you can transform y equals a cosine bx. For functions of the form y equals a sine bx and y equals a cosine bx, the absolute value of a is the amplitude, and 360 over the absolute value of b is the period. So let's look at that a value first. A in the front is the amplitude. So I say the absolute value, because I could change this to -2. Now it'll flip my graph over when I do that, but it won't change the amplitude. The distance from the center to the outside hasn't changed. So that is why we're talking about the absolute value of a is what's important. It doesn't really matter if I have a 2 in the front or a -2. It's that absolute value of 2 that tells me that that is the amplitude that I'm expecting. For the period, we have 360 degrees divided by the absolute value of b. So b in here is the one that's going to be right next to our variable. So let's compare a few things here. I'm going to do my sine of x, and I've got this in degrees right now. So we can see one full rotation ends at 360 degrees. Okay, then the next one ends at 720 degrees. So we would think that if we do sine of 2 times x, so 2 times whatever our angle is, well, if we expected on sine of x to finish our entire rotation after 360 degrees, if we put in 180 for this number, well, we're going to multiply it by 2 and we'll get to 360. So we're going to see our full rotation on this graph occur when we put in x is 180. Okay, and you can see that if we go up, down, and back up to where we started, we are crossing over at 180 rather than 360. We're getting there twice as fast because we're doubling whatever angle we put in there. Okay, so in the opposite sort of sense, if we had 1/2 x, we would, even if we put in 360 degrees for our x value, well, we would cut that in half to 180, and the sine of 180 is only going to give us 0 overall. We're not going to be done with our whole rotation until we get out to 720. Okay, so increasing the coefficient on your variable from 1 to 2 to 3, that is going to compress your wavelength down. You're going to have these long waves that have been kind of squished together like a slinky that's been pushed together. When you have a fraction, specifically a fraction less than 1 for your coefficient, that's going to kind of stretch that slinky out. It's going to pull those waves apart from one another because you're going to have to put in larger and larger values of x in order to complete that first full rotation around 360 degrees. Okay, so if we compared sine of x to sine 1/3 x, in the time it takes sine of x to go up, down, and up again, so kind of like 3 arcs, sine of 1/3 x has only managed 1 arc here. Okay, so our period is going to be 360 divided by the absolute value of b. So if we look at sine of x, well, the b value here for just normal sine of x, the b value is only going to be 1. So the period is going to be 360 degrees. That makes sense, right? We're going to go up, down, and up again in 360 degrees. However, if we have 2x, if we're expecting to get kind of everywhere twice as fast, then our period is not going to be 360 degrees. It's going to be complete after 180 degrees, which would be 360 divided by our b value. Now, if our b value is negative, that wouldn't change the period. So it goes down, up, and back down to where we started in the same period, whether or not that's negative or positive. It just changes the direction we start moving from. Final thing here is that we've kind of got a description of where we'd expect some x-intercepts to be for these graphs. So for y equals a sine of bx, so let's start with sine. We get our first intercept at 0, 0, when x is 0, y is 0. Our next one is at 180 degrees. So we have 1/2 times 360. Now for sine of x, our b value is just 1, so we're just doing 1/2 of 360 degrees. Okay, so that's 180. So at 180 degrees on the y-axis, we're at 0. Finally, at 360 degrees, we are at 0 as well. So that is when we don't have any b value. Now, if we have a b value of like 2, for example, and we are reaching all those same points, kind of like in half the amount of time necessary, or with half the angle, however you want to say it. For that, well, let's take a look for when we have 2x. So we would expect, based off this, we would still be going through 0, 0. Yep. We are going to get to our next x-intercept twice as fast. So rather than going all the way out to 180, we only go to 90. So that's because we're going to do 1/2 times 360 over 2. 360 over 2 would be 180, times 1/2 would give us 90. So we've gotten to that second x-intercept in kind of half the distance along the x-axis. Over here, we're going to get to our third one. Once again, we're not going to have to wait till we get to 360. We're going to get there, like I was saying, kind of in half the distance. So we're going to get there at 180. If we had 3x, we would expect to be getting to those 2 points in a third of the distance at 60 degrees rather than 180, and at 120 degrees rather than 360. You get kind of a similar thing that plays out with the cosine graphs. However, with cosine, your starting intercepts are not at right away at 0 and at the end of your full rotation, but it's kind of in between. So if you think of this as 1/4 of a rotation, 2/4, 3/4, and 4/4, well, then our intercepts are showing up at 1/4 of the way through the rotation and 3/4 of the way. That's why we say 1/4 times 360 degrees and 3/4 times 360 degrees. Now, if our cosine function has been changed around a little bit, like for example, if we do cosine of 3x, then we're expecting to get to those locations in a third of the distance. We're dividing that 360-degree number by 3. So we are finding, for example, in this one, 360 divided by 3 would be 120, and then times 1/4 would be 30 degrees. Okay, and there it is, our first intercept at 30 degrees. Our next intercept, which is going to be 3/4 of the way through our period, right? Our period in this one is 120. So 3/4 of the way through that should be 90. That's what we get when we do 360 divided by 3, so 120, and then we do 3/4 of that. Okay, so that is kind of it for our introduction to this lesson. We'll move on with example number 1 in the next video.